Welcome everyone to the session Testing API Resiliency using Kotlin, Leveraging Functional Programming at Scale by Naresh Jain. Naresh is the founder of Conf, the very platform that powers our functional conference. Beyond Conf, he is also founder and CEO of Specmatic, Agile India, and Zensio. We are delighted to have you with us, Naresh. Without further delay, over to you, Naresh.
All right. Thanks, Ritul. Thanks for the kind introduction. Pleasure to be here with all of you. I know it's Saturday for some of you and late night on Friday. So really appreciate you joining the session. Let's kick it off. I have a lot of content to cover, and hopefully we will be able to do justice to that. All right, so my topic is on API resiliency testing. And we've been working on an open source project called Specmatic, and we've been using Kotlin to pretty much build out the core functionality. And happy to be leveraging a lot of functional programming aspects in it. And so that's kind of what this talk will be. So the first part of the talk is just introducing the problem space in terms of API resiliency and how we do API resiliency, what it actually means, and like look at some demo in action so we all get on the same page in terms of API resiliency. Then we're going to talk about one specific challenge that we ran in Specmatic, and then how did we leverage sequence or lazy lists and monads to kind of help address that particular problem for us. So that's kind of really what the talk is all about. So let's jump in, but let me set some context before we go in. Why is API resiliency testing important? I'm sure the whole CrowdStrike incident is fresh in people's mind. Of course, that was not caused by API, being down. However, it was important to understand the snowball effect that it created, including, airlines not being able to board passengers, to hospitals not being able to figure out what, medications they need to give to patients. So, the point I'm trying to make is that today we live in a very, very connected world. And even an outage in some place can actually have far-reaching consequences, which is why resiliency in general for applications becomes extremely important. But API resiliency testing, which is specifically the focus of this talk, is what we're going to click in. Not so long back, I don't know if you saw this news where basically Bing's API was down, and while Bing's API was down, you would assume that Bing would stop working, but actually it took down along with it Microsoft Copilot, DuckDuckGo, ChatGPT, a whole bunch of other things that depend on Bing's API, right? So again, the point is that if one thing goes down, it has a snowball effect on a whole bunch of other services. This one is kind of one of my favorites where, you can see how this might actually impact you on a day-to-day basis. So, this is a little dated, but still quite interesting, is there was an outage on basically Tesla's API, and that basically avoided from patients to basically being able to log in, basically get into their cars. They were locked out of their cars, right? So as and when we are more and more relying on essentially technology to power our lives, these kinds of outages can really be very problematic for people. So I hope that kind of helps you understand the importance of resiliency in your APIs. And so now let's look at what can we do to make our APIs more resilient, right? And so, like a good engineer, I asked GPT, what should I do for resiliency testing? And this is kind of what it gave back. Negative functional testing is important, like boundary value analysis, invalid data types, overflow, underflow conditions, right? Sure enough. Service dependency testing in terms of like both backward compatibility and contract testing, chaos testing, where you may want to inject faults basically do network partitioning or other kinds of things and see whether your APIs or your application continues to perform well. There will be, again, performance related aspects where you may want to do load, stress, soak, other kinds of tests to make sure that the application continues to perform well. And finally, security resiliency testing, from SQL injection to DDoS attacks to all of these various things might be important. And of course, as all of you know, observability monitoring and alerting are very important, and you need to test those things as well. So when things go wrong, these things will fire up and give you the right signals. Right. So there's a lot in terms of resiliency testing that one needs to do. And I'm honestly not sure, at least based on my experience working with several companies, I don't see many companies, having a comprehensive coverage on all of these different aspects of testing, right? I don't know what your experience is, but at least I've not seen many companies very serious about this. And there are several reasons why this is a neglected aspect. From skills, from access to the right tooling, to basically having the time and focus on things like this. So the challenges can be a lot. But what we tried to do, at least with Specmatic, was to try and take a stab at addressing at least some of these with a no-code solution, so that basically when people don't have time or don't have the necessary skills, they could still leverage this open source tool to kind of achieve at least part of the resiliency aspects, especially around the service dependencies and the negative, the negative functional aspects and so forth. So let's jump in. Let's look at a specific example and see this in action, and then we will peel the layers of the onion to understand what's going on under the hood. All right. So I've presented a very simplistic architecture here that I'm hoping all of you can relate to. You have an app talks to an order service. The order service then in turn talks to a product service, and it then logs all the stuff that the request responses onto a Kafka topic for analytics. And this is obviously, no company probably has this simplistic architecture. It is way more complicated, and if you're in the microservices shithole, then you would have hundreds of these flying all over the place, right? Today, let's focus on basically testing, the resiliency of the product service in isolation, so that we can at least be sure that this Lego block or this building block works as expected. You could obviously then individually test each of these, and that's kind of our approach. Is you would test each of these Lego blocks in isolation, make sure that they are working as expected, then bring them together and kind of do more, higher order tests around this. Right. So we start with basically testing the resiliency of the product service itself. So let's jump in and look at a live demo of how we do that. I'm going to quickly switch over here to IntelliJ. I have a very simple app that essentially it's a Spring Boot app written in Kotlin, and it essentially has an API spec. This is my Open API spec. We can look at it. It's very simplistic. It has a /products path that it's exposing, and it has two basically methods: the get to retrieve the products, and post to create a product, right? And so what we want to do is basically make sure that this particular service that is adhering to or implementing this API specification is behaving as we expect, right? So I have a little contract test that I have written here, and let's try and run this contract test and see what happens. And as you can see, it's basically bringing up the API itself. So it's a Spring Boot application. So it's basically bringing up the API. And then it essentially made two API requests, one for the post and one for the get. Let's see what actually happened here. So it basically made a request on localhost 8090 a post on /products and sent this payload, name, type, inventory, and cost, and received a 201 response back with an ID 0. And according to our contract test here, this test has passed. It meets all the criteria, right? This meets the criteria that is defined in the API specification. Because again, if we go here and look at the test itself actually is pretty empty, right? All it has is a before all and an after all method. There's actually no tests at all. For those who are familiar with the tests at test annotation, there's actually no test at all. All it's doing is just defining some properties in terms of where things are, bringing up the application, and finally shutting down the application. So where are actually all the tests coming from? The tests are basically being generated by Specmatic by looking at this config file, this spec file, and essentially generating the contract test from it. Right, there is a little Specmatic YAML file which simply tells where to find where to find the specification, and it picks up the specification from there. So that's basically what's happening here. And let's look at another test, which is the get test. And so here we've tried to do a fetch on /products of type gadget. And we've got back the product that we just created, right? So it's an array of products, and we got one product back, the product that we just created over here. So that's simple. It looks fine. It's all good, right? But this is not going to give you any kind of resiliency and making sure that the application is working as expected, right? So let's turn on some knobs here and see if we can make this a little bit more fun. So I'm going to start off by basically turning on only positive tests. Let's quickly give that a run and see what happens. So far we have 2 tests, and there we go. Let's see what happens. Of course, how did these 2 tests come? The 2 tests were basically picked up from examples that were given in the specification. So you will see here there is an example that is given, and that's what was picked up by Specmatic to create the request and the response, right? Like basically to create the request and validate the response. So the first 2 examples were picked up from here, but now we've turned on one knob, and that you can see has generated from 2 tests, we went up to 53 tests. And you can see these are all marked as positive scenarios because we have right now only turned on positive tests. And what this means is that basically, let's look at some of these requests, right? So here is a post. We saw this before with iPhone gadget and this and an ID 0. So that's good. Now what we see is another request was made, but this time instead of gadget, which is what it had used last time, it's using book as a type, right? And you can see it kind of iterates through all the different enums that we have. So there's a list of enums that is defined in the spec. Let's quickly go to the spec and have a look at the enum. So here we have for product type an enum book, food, gadget, others. And so what it's trying to do is basically iterate through each of these enums and trying to validate if all of those are working. And at this point, it's all just validating the expected behavior, right? These are all positive scenarios. So it's just going through and basically looking at all possible values that can be, that requests can be made, for which you should be getting back a valid 201 response in this case, right? There are also other interesting things it's kind of doing in combination, which is basically it's trying to play around with the inventory. So you would see that the inventory size is different in each of these. Here it's also interesting, it's passed cost as null, and it's trying to make sure that cost can be null or not. Why is cost being passed as null? Because if we go here, in the spec, it said that cost is a nullable field, which means someone could basically not pass cost at all, or even if they passed cost, it could be null. and your application is supposed to handle that, right? So all these subtle things, often in my experience, developers won't have time to basically sit and write these kind of exhaustive tests, right? And so at this point, what we have done is we've tried to exercise all the different possibilities that exist in the specification. So right from whether something is nullable or not, there is a min and max range, whether your application is handling correctly the min and max range. So you'd see some requests were made with, inventory 999. So we're trying to test, the edge and make sure that the application can handle all of that. And, all of this without writing a single line of code, right? You're basically just, leveraging the API specification as the source of truth. And when we built this out, we essentially took inspiration from property-based testing, where we're taking the spec, deriving a set of properties out of it, and then creating generators that generate all of these combinations for us and making the request and validating this, right? So that's kind of what is happening. This, in my opinion, is still okay, right? Like this is all positive tests. It's great. We have 53. But it's not the whole thing, right? Like for me to be confident, for me to go back and sleep at night confidently, I would actually want to also test a bunch of negative scenarios, right? So let's look at, let me turn on the resiliency side of things, where we will kick in a bunch of negative tests as well. Let me just run that, and then I'll explain what happens when we do that, right? So yeah, it's just bringing up the Spring application, and there we go. It started firing the requests, and we've gone way beyond the 53 now, right? And whoa, okay, all right. So we have 351 tests, and all 351 tests have passed. But you can now let's double click here and see what's just happened. So there's a whole bunch of positive tests which was there before. So that's great. And here you start seeing some negative tests have started popping in. And in fact, if I expand this, you would also see the explanation for what the negative test is. So here we are basically saying the request body name string mutated to null. All right. So basically, we know that the string, the name in the body, which is a string, is a mandatory parameter, and it always has to be present. But what we are trying to do here is we're saying, okay, I know the property says that this is a mandatory and should always be supplied, and it's of type string. But what happens if I pass a null, right? If I pass a null, I would expect a non-4x, basically a non-200 response to come back, basically a 404, a 400, sorry, response to come back, a bad request, 400 bad request to come back. So it now tries to validate this, right? So what you will see here is a little bit of a combination of property-based testing and again a deviation or a alteration of mutation testing, where we are trying to mutate some of the things and also change the expectation. So if I send name, I should be, if I send name a proper valid name, then I should get a 201 response. But if I send an invalid name, then I should get a 400 response, right? So it's kind of deriving properties from the base set of properties using inspiration from mutation testing and kind of constructing a whole bunch of tests around this. And so you'd see that it actually goes through, it tries a whole bunch of combinations with this being mutated to null, then it being mutated to a number. So we're playing around with different data types. You'd also see in some places where the inventory, we're playing around with the inventory, where we might change the inventory to a number outside the range and make sure that that is not accepted. So these are all with inventory still, this thing. Let's see. There's also it playing around with the type itself, where it changes the type and so forth. So anyway, you get the idea. The point is not to dwell too much on this. You get the idea that what is basically going on. I could also go here, just refresh this test, and you'd see that this is a report that gets generated when I run these tests. 351 tests were run, and you kind of get a little bit of a visual way to look at it in terms of, okay, it has a slash products, it has post and get, and inside this, there are two possible responses, 201, 400, 200, and 400 for get. And then it's generated 296 tests for the 400 cases, and you can actually go look at each of these tests. What was the request? What was the response? So gives you a full drill down of all the different things that it's played around to come up with the solution. So hopefully that kind of made sense to everyone. Let me kind of quickly jump ahead and explain how did we derive these 351 tests, right? So why 351 tests? How did it come up with 351 tests? So as we know, there were 4 fields: name, type, inventory, cost, and their respective data types. These 3 were required while cost was optional. These 3 were non-nullable while cost was nullable. Obviously, name didn't have any other constraint, but type, the type had an enum, which was of book, food, gadget, and others. And inventory had a min and max of 1 and 999, and cost had a min of 0.00, right? So these were all the constraints. Now, okay, based on this, how did we come up with the numbers? So if I look at it, we derived a set of positive variations from it, which is for name, it's only string is a positive variation. There's not much, but for enum, there are 4 possible values, so we can play around with that. For inventory, we have the min and the max values and 1 random value in between the min and max. And then for cost, we have 0, which is the min value, a random value, and then null, because null is also valid. And then there were a set of negative scenarios, which were basically changing the data types, changing the boundaries, testing with negative numbers and so forth. And so if you look at the variation count for each of them, you have 4, 7, 8, 7 respectively. If I did a pure permutation on this, right, then I would end up with 156 different possible tests. Okay, but that is going to be too many tests, and this is even like a very simplistic API. I don't think anyone has such simple APIs, right? And so what we've done in Specmatic is actually taken this and deduced them down, right? Try to look at some kind of ways in which we can reduce this down using a little interesting algorithm, and we bring it down to 351 tests, which still gives us the full coverage, right? So this is great, all good. But what's the problem, right? Why am I giving all this context, right? So I want to now jump in and talk about a real world situation where hopefully this gives you enough context of the problem space, right? What we are trying to do, the combination that we will explode with on a simple problem. Now let's take a real world example, right? This is from a telecom domain. Again, a very simplistic actually API. It's a trouble ticket when someone in the telco domain has a problem. They go ahead and raise a trouble ticket, and this spec for basically creating and managing a trouble ticket is only 4,430 lines, right? The spec alone. Okay. This is actually one of the simplest APIs that we work with. Most of our APIs are 9,000, 10,000 lines in terms of the spec itself. Okay. And then if I took this API and ran Specmatic on this, what you would find is, with just about 9% coverage, you would end up with about 5,000 tests, right? And there's a lot of things that are still not covered. So if we expanded all of these, this can easily go to about 72,000 tests, just for one simple API, right? Like these are the kind of complicated APIs. And as you can see here, only 724 tests have passed out of the 5,263 tests. A lot of them have failed because not many applications take this this aspect seriously and end up basically leaving a lot of things not validated or not covered. So obviously this is a functional issue, but also a security issue. And so this is kind of the kinds of problems we deal on a day-to-day basis, right? Where we have very massive, complicated spec. We try to generate tests out of them and then try to validate whether these work or not as expected. And every once in a while, we used to end up with this problem, right? Which is a classic combinatorial explosion of tests, and then we run out of memory. I hope this is kind of familiar to folks in this space when you're trying to do this kind of a combination and your specs start getting more and more complicated. Very soon you kind of end up building like so many possible scenarios, and then you end up with out of memory, right? And if you dig in deeper on this particular application, we had given 4 GB memory, and you can see that after just about maybe 2 minutes, maybe less than 2 minutes, it actually exhausts all the memory, and we basically plateaued out. Basically exhausted the complete memory, the heap memory here. And also you'd see that a pretty massive spike on the CPU as well as we are running the GC, right? So a lot of garbage collection going on. And this is not great, right? And if you dig in terms of what's happening, what you will see is we take the spec, we convert those JSON objects into JSON patterns, and that's what we use for these combinations to create these combinations. And the JSON object itself under the hood is holding the key values in a linked hash map. And so that's starting to basically explode, and we run out of memory. So this is kind of the problem where we said, okay, this is clearly a challenge because certainly we want to deal with really large and complex specifications. So we cannot just keep expecting to bump up the memory. We need to change the way we are doing things. So this is now I'm showing you after us using lazy lists and monads, how both the heap memory and the GC CPU have pretty much stabilized, and we don't seem to exceed the available memory even on really large, even more complex specifications, right? So what actually happened, right? What did change here? So as I was showing you earlier, when we do a test execution, there's actually nothing inside the test itself. What we are doing is we are basically creating a dynamic JUnit test factory, which essentially builds a request generator. And that basically derives all the properties and creates the request based on the Open API specification, and then makes the request to the API. When you get a response back, it then validates the response against the API spec to make sure that the returned schema is as per the specification and so forth, right? So when we are doing this process, we are obviously generating a whole bunch of tests to feed dynamically into this test factory, right? JUnit test factory. So let's look at what we were doing earlier and the classic rookie mistakes that we had made and how we try to fix them, right? So we have the test factory here on the right. There is an Open API specification on the left. Then there is basically what Specmatic does is essentially reads the spec, converts it into scenarios, builds out all the different data types that are there in the specification, the components that exist in the specification, creates a set of patterns from which we can then generate all the possible values for our resiliency tests. And that as it's doing that, it's basically also validating the examples, it's validating a whole bunch of things, and as it's going through that, there are a lot of cases where you end up in a situation where the example that was provided is not valid as per the spec, and we can't proceed. So it would basically throw an exception, and then that exception would essentially kill the whole process and essentially generate a report and fail the test execution, right? But let's assume that no exceptions were thrown, then you get a complete list of all the tests. And that's obviously the first problem, because when you try to do a complete list of all possible tests, we run out of memory and we end up with these problems. But there were several reasons why we had done the way we had done. I'll explain that in a minute. But there is more to this whole pipeline in terms of test execution, right? There are a set of filters that kick in, right? Which basically there are ways to filter certain things and stuff like that. So there was a filter that would actually, or a set of filters that would actually give you a filtered list, and that's what would then get fed and executed in a sequence, almost in a loop. Each of the tests would get executed, and finally, actually not even finally, as the tests are executing, you may also then further get exceptions. So for example, if the API is down altogether, no point executing further tests, right? So I might want to do an early fail out, right? So at each response level, there would be a validation, and if that would fail for certain criteria, then basically we would bail out and stop the execution. If it's not a critical issue, then we continue, but there are some cases where we bail out. So there's still like a lot of these conditional logic to decide to resume the execution or to stop the execution. And finally, if everything went well, then we would generate a report, right? So there was an eager list that we were using. There were try-catch blocks we were using all over the place. And this is kind of where we were ending up with out of memory, right? And so obviously the question is, why, I mean, this is pretty common knowledge. Why are you using a eager list here, right? Why not use a lazy list? And I think that's a fair question. In retrospect, it kind of makes sense, but debugging, a sequence or a future is a bit more complicated than having a deterministic list that you can think. There's also things like, there was a contributor called Steve West who had contributed a fix where he wanted to control only certain depths in certain areas of the execution. And so there were these other kinds of things that required the list to be available so you can apply the depth and other kinds of criteria on how the list is getting generated. So there were, and lastly, we also wanted to first compute the total number of tests and maybe not even execute the test, because if your spec is very loosey, not well defined, then you would end up with a million tests, and we didn't want to go and waste the CPU cycles in executing all of that. So there was reasons why we ended up with a eager list. However, because of the memory issue, we had to change that. And if you look at the current implementation that we have, this is kind of how we have redesigned this. So similarly, we build the scenarios, etc., but those are getting converted into a lazy list, basically a sequence in Kotlin. The filters are also attached to this, and they all get evaluated just in time. So this is at this point essentially a sequence that is fed in, and at this point, like you can see, very minimal memory usage, and that's then wrapped into either monad and then given to the JUnit factory to execute. And as it executes, because it's a monad, if there are failures, then we basically mark it as a failed test but continue the sequence, and finally publish the report. So what you can see compared to before and after is, we don't have the eager list. The second is obviously we don't have these exception blocks that are spread all over the place. Now all that logic is nicely encapsulated in the either monad, and it's kind of nicely available in one place. So that's kind of a quick before and after, if you will. There's actually a lot more complications that exist, but I've tried to simplify it to kind of just explain how we changed from what we had earlier to what we had now. Quite heavily using a lot of the maps and things like that to try and streamline the whole pipeline here. We think of this as a test execution pipeline. So a lot of that is being treated as a stream, and execution is simplified now. Maybe I think I have only a few minutes left. So maybe I'll quickly stop here, see if there are any questions, and then maybe we can jump into a code walkthrough. I'm guessing
There is one question from Yogesh.
okay.
He says, noob question, but What is the fundamental difference between lazy list and eager list?
So basically, if you look at a eager list, in that we would actually be constructing the test objects, the test cases, and all the evaluation for those test cases would happen upfront. And then that's when the list would get created. This is where the patterns are evaluated, and the patterns are evaluated as in we take the examples, we explode that with all the different possible data types and so forth. So we expand all of those and pre-compute the output from basically the patterns. And in that's in the eager list case, right? In the lazy list, none of this has happened until actually the test is about to execute. So when you actually execute the test is when it would evaluate the patterns, it would generate the permutations, and those are the ones. Then also there is like a filter. So basically you would ask for next. If the filter is successful, it would return, else it would just keep doing next internally till it finds one of the patterns that matched and that is valid for execution. So none of these is eagerly evaluated upfront, which means we don't have to build this entire tree of all objects in memory and then apply a filter on top of it. Those are all just expanded and evaluated at execution time. So that's kind of the difference between the eager list and lazy list in our case. So we are using sequence in Kotlin, which is equivalent to kind of a future list kind of a thing. So it's a list of futures. None of those are evaluated until you actually execute them.
Got it. I hope this has answered your query, Yogesh.
I will be happy to take questions further in the Hangout room. So thanks again for joining this session and look forward to seeing you in the Hangout area.